So I'm going to be talking for the next 45 minutes or so about the JUICE mission. So JUICE stands for the Jupiter Icy Moons Explorer, and it's a European Space Agency mission that's going to travel to Jupiter and its moons. And as many of you, I'm sure, are very aware, we're only a couple of weeks, actually less than 2 weeks away from the planned launch of JUICE, so it's a particularly exciting time. So very briefly, this is where I work. So it's University College London's Mullard Space Science Laboratory. So we're based out in the Surrey countryside. So we are a full part of UCL, but our department is off-site. And we have roughly 170, 180 staff and students based there, and with the largest university-based space science group in the UK. So we build instruments that fly on various missions, and we study the data that are returned from these missions. So not just with the European Space Agency, also NASA, Japanese Space Agency, collaborating with colleagues in China as well, and across the world. So some of the planetary missions we've been involved in, I won't go through them all, include the Giotto mission to Comet Halley. That was ESA's first planetary mission. And then more recently, the Cassini-Huygens mission, a joint NASA, ESA, and Italian Space Agency mission to Saturn. We're building the primary camera for the ExoMars Rosalind Franklin rover, and Comet Interceptor is an exciting mission close to my heart that will be launching in 2029. So today, I'm just going to concentrate on JUICE, of course. So to the absolute basics. So where is JUICE going? Well, JUICE is going to the planet Jupiter. This is a view of the inner solar system. So we've got the sun in the middle, and then moving outwards, we have Mercury, Venus, and then Earth, and Earth's orbit is shown in red. And then beyond the Earth is Mars. And if we zoom out further, we see the outer solar system. So the slide before is in the very middle of this view. So Jupiter is next, so it's about 5 times further away from the sun than the Earth is. And then we have Saturn, Uranus, and Neptune. And these 4 outer planets are gas giants. So unlike the Earth and the other inner planets, the terrestrial planets, they don't have a meaningful solid surface. What we see are the cloud tops, and if you were to go into the atmosphere, you just fall through an atmosphere that was getting thicker and thicker and thicker, and you'd be crushed under the heavy pressure of the atmosphere before you'd reach any solid surface. That's why they're called the gas giants. So spacecraft have visited all of these planets by now, plus Pluto, which used to be a planet, but it's not classified as such yet. And JUICE is going to Jupiter, as I mentioned. So we'll start with this not very good photo of Jupiter and its moons I took recently. So this happened to be a night where the 4 largest moons of Jupiter were arranged in a line and in the order of distance from Jupiter as well. So that the faintest point at the upper left is Callisto. Then we have Ganymede, then Europa, and the closest moon to Jupiter is Io. You can just about see a couple of faint lines across the surface of, or the cloud tops of Jupiter. So this is probably similar to what Galileo Galilei could see with his basic telescope a few centuries ago. So you can, if you know where to look, Ganymede is just about visible to the naked eye if you have fantastic vision, but usually you need binoculars to be able to see these. But you should be able to see these 4 moons of Jupiter with a good pair of binoculars or a small telescope. And because Galileo is the one who found them, they're now referred to as the Galilean satellites, or the Galilean moons. They form a mini solar system. So Jupiter and its moons are like a miniature solar system. All 4 of these large moons are roughly the size of our moon or bigger, and Ganymede is actually larger than the planet Mercury. So if we send spacecraft to the Jupiter system, we're not just learning about Jupiter itself, we learn a lot about these amazing moons that Galileo first noted several centuries ago. So Jupiter, as most of you will know, I'm sure, is the largest planet. So these are all the planets to the same scale in this Planetary Society graphic. So you can see at the upper left, we've got Mercury, Venus, Earth, and Mars. And then underneath Mars, the furthest left of the large planets is Jupiter. And you could fit 10 Earths side by side across its diameter. So it's basically 10 times wider than the Earth is. So occupies a much larger volume of space than the Earth. It's got a very strong gravitational field. It's also very important for the whole solar system because it controls the orbits of lots of asteroids and comets. So it's responsible for changing the orbits of many comets over the few billion years of the solar system's history, and it's probably thrown a few comets and asteroids in the Earth's direction, resulting in impacts in the past. And then on the right, of course, you've got Saturn. So its rings are obviously much bigger than Jupiter, but the planet itself is smaller than Jupiter, and then Uranus and Neptune. So I showed you an image of Jupiter already taken from the Earth. There are obviously far better images available of Jupiter and its moons taken from the Earth. But we learn the most about these planets by sending spacecraft to them. So we either fly past the planets and its moons, or we go into orbit around the planet, and then we can study it for a few years rather than just a couple of days, which is what happens with a flyby mission. And this was the first spacecraft to be sent to Jupiter. This is Pioneer 10. You can see it being built there at upper right, and on the left is an image returned from Pioneer 10. So when we look at Jupiter from the Earth, we can't see the night side. We can only just about see the one edge of the night side. But generally, we can only see Jupiter from the same direction as the Sun. So Pioneer 10 crossed the asteroid belt for the first time. It wasn't clear beforehand whether it would be able to do so safely, but it did, and returned these first close-up images of Jupiter in the early 1970s. As well as Pioneer 10, there was a twin spacecraft called Pioneer 11, launched shortly afterwards. And Pioneer 11 returned very similar images and other data from around Jupiter. And it was decided by NASA to send Pioneer 11 onto planet Saturn. And to do that, it had to basically leave Jupiter flying away over its poles. And so it gave us a really unique view of Jupiter looking down from close to one of its poles, a view that we wouldn't see again until much more recently with the Juno mission. So, so these spacecraft and the others I listed, they don't just take pictures. There are also other instruments on board measuring things like the magnetic field. So that's the direction of the magnetic field. So like a compass, but not just the direction, it tells you the strength of the magnetic field. It also can detect particles, so ions, electrons, etc. And we can detect radio waves and other emissions from the planets. So a few years later, we had the Voyagers 1 and 2 spacecraft, and both of these spacecraft went past Jupiter and its moons in 1979. We had some fantastic data returned from these two missions, and as many of you will know, they went on to explore other planets in the outer solar system. But it's from these missions we got the first clear images of the rings of Jupiter. So at the bottom right there, you can see a view of the rings viewed from the dark side of Jupiter. So a view that you can't get from the Earth. So it's only very recently that we've been able to get images, good images of the rings of Jupiter from the James Webb Space Telescope, looking from the vicinity of the Earth. And it's from the Voyagers that we got the first really good images of the moons, and it revealed, or both spacecraft revealed these moons to be amazing worlds in their own right. So on the left here, we have Io, very bizarre world covered in volcanoes, always erupting. And it's data from the Voyager 1 that revealed Io to have active volcanoes. So it looks like a pizza. That yellowish color is from lots of sulfur that's been thrown onto the surface from its many volcanoes. And then on the right, we have an image of Europa from Voyager 2. So what you're seeing on the surface of Europa is very different to the extremely hot surface of Io. Basically, what you're seeing here on the right is a world covered in water ice. So everything that you're seeing is frozen water. Because Jupiter and its moons are so far from the sun, it's much colder there. So the water ice is very common and forms the crusts of most of the moons of the outer solar system. So you can see lots of cracks on there as well, hinting that the crust has changed over time, and we'll come back to that later in the talk. So JUICE isn't the first European spacecraft to visit Jupiter. The Ulysses spacecraft, which was sent out to study the sun, also went past Jupiter, but it didn't carry any cameras. It did return some amazing data, but we only have an artist's impression of what the Ulysses flyby was like in 1992. And then we had 2 further flybys. All the missions up to now have been flybys. They've just gone past Jupiter and its moons at high speed, gathered as much data as they could, and sent it back to the Earth. So Cassini, on its way to Saturn, took amazing pictures and gathered other data from Jupiter in the year 2000. And then the New Horizons spacecraft, on its way to Pluto, took data from Jupiter and its moons again. And here is an amazing view of Io. And the volcanoes I mentioned, you can see a couple of them erupting here. So that big bulge at the top is actually an erupting volcano throwing material out into space, and it's falling down like in the shape of an umbrella. You can also see another volcano on the left. And on the night side, on the right-hand side of the view, you can see a couple of volcanoes with material being thrown into space there as well. So to really study a planet and its moons in detail, you need an orbiting spacecraft. So rather than going past at high speed, it slows down and goes into orbit. So we'll operate for several years, gathering data to send back to Earth. And the first Jupiter orbiter was called Galileo. This was a NASA mission, and it arrived at Jupiter in 1995 and operated until 2003. So it was an incredibly ambitious mission, and it delivered a probe to the atmosphere of Jupiter. So at the center at the bottom there, you can see the probe entering Jupiter's atmosphere, and it worked brilliantly. It didn't have a camera on board, but returned really valuable scientific data about what the clouds of Jupiter were made of, the atmosphere, looking for how the pressure changed with depth into the atmosphere, etc. And it radioed that data back to the main spacecraft. So Galileo overall worked brilliantly, but there was one unfortunate problem. So the main radio antenna, so the way it communicated with the Earth, it was supposed to open out like an umbrella because it was launched from the space shuttle and it needed to be folded up for launch. Unfortunately, that umbrella-like antenna didn't open fully. So you can see on the left of the picture of the spacecraft, a few of the ribs of the antenna unfortunately got stuck. So Galileo wasn't able to send all its data back to Earth. So it could only send it back at low speed through a small antenna. So we couldn't get all the data that Galileo gathered back to the Earth. But nevertheless, Galileo was still incredibly successful, especially given its unfortunate limitations. So we got amazing views like the one on the right of the moon Europa, and you can see some of those cracks on the surface of that moon in much more detail. And then we have a spacecraft orbiting Jupiter right now. The mission is called Juno. It's to study Jupiter itself, not the moons, and it's been returning great data about the atmosphere, the aurora, and the interior of Jupiter itself. Occasionally it does go past a couple of the inner moons, and I'll show you some of those images later. So we have had many missions going past Jupiter and its moons in the past, and these four views show how our understanding of the Jupiter system has changed over time. So at the top, you've got a sketch of Jupiter and its moons. Galileo noticed that the moons moved from night to night, and he realized that these were in orbit around Jupiter. And then fast forward a few centuries, we've got the first low resolution views of Europa from Pioneer 10, quite blocky, as you can see. Then Voyager 2 returned the view there at the center in the bottom, and then Galileo returned some amazing data, as you can see here on the right. So JUICE stands for Jupiter Icy Moons Explorer, and as the name suggests, the main aim of JUICE is to explore the moons, but it also studies Jupiter itself. So as you can see from this artist's impression, it's got big solar panels. So it's only Juno, which is orbiting Jupiter now, and JUICE, which have had solar panels for exploring Jupiter. Up to now, we've had to take basically plutonium radioactive source on the spacecraft. So Pioneer, Voyager, etc., all of those missions carried plutonium powered source. So JUICE is going to be solar powered like Juno is. So during the rest of the talk, I'll provide some background to why we want to study Jupiter and its moons, and then I'll come on to the instruments that JUICE is carrying, and then the mission that will soon start less than 2 weeks from now, if all goes well. So JUICE has been under preparation for a long time. So it sort of started in 2007. So this is an ESA slide. So you can see it's split into 4 phases. So from 2007 to 2014, there was a call for mission proposals. There was a study of what the spacecraft would look like, what instruments it would carry. And then the instruments teams proposed to build experiments to be carried on the mission. And then mission adoption happened, which is this formal step that has to be taken with European Space Agency missions, where all the member states support going ahead with spending the money on building the spacecraft, launching it, and the member states of the European Space Agency promising to pay to build the instruments. And then we had the development phase, so building the spacecraft and the instruments, putting them all together, and that's culminated in the last few weeks with the JUICE spacecraft arriving at the launch site, and will be paired with the rocket very soon. And then we're right in the middle of this plot. We're at the time of launch, only a few days away. But getting to Jupiter will take a long time. So after launch next month, it will only arrive at Jupiter in 2031. So it's going to take a while to get there. I'll explain its path a bit later. And then it will spend several years exploring the Jupiter system, going into orbit around the moon Ganymede itself, and then maybe the mission will be extended depending on how things have developed. Okay, so why JUICE? Why build this spacecraft, and why decide to concentrate on some of the moons of Jupiter? So this shows many moons of different planets in our solar system. So at the upper left, you can see Earth's moon, which we're all very familiar with. And then for most of the other planets, the moons are much smaller. So you see for Saturn in the middle there, it has one very large moon, Titan, and Neptune has quite a large moon called Triton. But for Jupiter, we have 4 very large moons, so roughly the size of our moon or larger. And Ganymede is actually larger than the planet Mercury. So by sending a spacecraft to Jupiter, you're not only going to learn more about the planet itself, but also about these 4 large worlds themselves. So these 4 large moons, as they're going around Jupiter, they follow very curious paths. They're actually in phase. So you can see 3 of these moons shown here. So on the left, we're looking down at the Jupiter system. So Jupiter's in the middle, and then we're showing the orbit of Io, and then Europa, which orbits a little slower than Io, and then Ganymede on the outside. So Callisto isn't included here. But for every 2 orbits that Io makes around Jupiter, Europa makes 1 orbit. And for every 4 orbits that Io makes, Ganymede goes round once. So they're all in sync with each other. And so occasionally they line up. And when this happens, Jupiter's pulling, its gravity is pulling each of these moons in one direction, and another moon is pulling in the other direction. So this means that Io, the closest moon to Jupiter, is being stretched very frequently and by quite a lot, which releases a lot of heat in the interior of the moon, and that's why Io has so many volcanoes on it. It's due to tides in the moon. Europa, there's a fair amount of heat being released as well, but that's less than the amount of heat being released on Io. That's why Europa is believed to have a liquid water ocean under its icy crust. And then Ganymede as well is being heated to a certain degree by these tides as well, but less than the other 2 moons. So as you go further away from Jupiter, these tidal effects get weaker. So Io is being heated a lot, hence the volcanoes. Europa is being heated quite a bit, so some of that ice is being melted. And Ganymede, we think that it has a liquid layer as well, but probably much deeper than the one at Europa. So on the right, you can see one of these moons being stretched regularly as it goes around Jupiter. So it's not quite that extreme, but we're still talking about the surfaces of these moons, especially Io, being lifted by tens of meters by the tides by Jupiter on one side and the other moons on the other side. So Europa. Europa is really fascinating because, as I've already mentioned, it's got this icy surface. And one curious thing about Europa is it has very few impact craters. So if you look at the Earth's moon through a telescope, you can see that there are countless pits and craters in the moon, and these are caused by asteroids, comets, and other bodies hitting the moon. So the older a moon is, the more craters it has on the surface. And Europa has very, very few impact craters. And that means it's quite a young surface, which means that the surface has been changed relatively recently. So we're talking about probably hundreds of thousands, if not millions of years. So that's very, very long time for us. But in terms of geology, that's very recent. There are also strong hints that there might be ice volcanoes on Europa. So at the top there in the middle, you can see an observation made of Europa suggesting that there's water being thrown out into space. And there could be a very thin crust with a liquid water ocean underneath. So here's a close-up view of Europa. So I mentioned these cracks before. So you see along these cracks, you see these brownish patches, and it's thought that this icy crust sometimes splits open, water from underneath escapes into space, and it carries some chemicals with it, so salts and other chemicals, and these settle on the surface, and that's why you get these brownish patches in places on Europa. And if we look closer at the moon, we see some more features. So this is one of the few impact craters. So it is the largest one, actually. And I like Europa because it's got Welsh place names. And this crater is called Pwyll. And you can see that it's smashed into the icy crust of Europa and scattered ice in all directions. And you can see it's younger than some of the other features. You can see those white streaks covering some of those brown patches that have come out of the cracks. So we can tell the relative ages of some of these features. On other areas of Europa, we see what look very much like icebergs on the Earth. So ice flows that we see in the Arctic and Antarctic. These look very similar to what we see on some areas of Europa. And actually, if you print out this picture and cut out all the individual bits, you can rearrange them and see that lots of these features did line up better in the past. So we can see from here that either there was open water at the time, so parts of the crust have been warmed a lot in the past, so there possibly was open water exposed to space, and these blocks of ice, these icebergs, are moving around. Or an alternative is that this ice, if it's got lots of salt in it, it might flow very slowly like glaciers do on Earth. And maybe this rearrangement of ice isn't icebergs bobbing around in open water, but more like a flow of slushy mud moving bits of the surface around. We don't know this, which of these two scenarios it is yet, but clearly parts of Europa's surface have been changed over time. Here we've got hints of ice volcanoes as well on the surface of Europa, so it's a really fascinating moon. So we're sure that there is a global water ocean under the surface of Europa, but we don't know whether it's like the picture on the left, a very thin ice crust with liquid water getting very close to the surface, and maybe volcanoes on the sea floor, or if it's more like the picture on the right with a thick ice crust. So you get bubbles of warmer ice coming up to the surface, but it takes place over thousands of years. So and that might explain these cracks. So JUICE will help answer that question. So we'll know what the depth of the ocean is, the thickness of the crust, and what the possibilities are for life under the surface. And yeah, as I mentioned before, we have tantalizing hints that the ice volcanoes on Europa are erupting now. So maybe there are some places on Europa that are throwing water into space as we speak. And we'll learn more about these processes, whether they're occurring now from JUICE. So next we come to Ganymede, which is a moon, as I already said, which is larger than the planet Mercury. Surface temperature between a minus 120 and a minus 180 degrees Celsius. It's believed to have a water ice layer under its surface as well, but much deeper than on Europa. And what's very special about Ganymede is that it has its own magnetic field. So here on the Earth, if we take out a compass, it points towards north. If you were to take it to Jupiter, it's got a magnetic field as well. On that planet, it points towards the south, but it's a planet with a global magnetic field. So not all planets have that. So Venus and Mars don't have a global magnetic field. So Ganymede does have a magnetic field, and it's in orbit around Jupiter. So it's a fascinating place where we have this big magnetic cage around Jupiter extending out into space, and embedded within it, we've got Ganymede with its own magnetic field as well. So we're looking forward to being able to study that, learn more about it, and maybe understand how it's being generated. So Ganymede also has surface features. It does have lots of impact craters, but it has some relatively young patches on its surface as well. You can see cracks where the crust has broken open in the past, and possibly flows of liquid or at least slushy ice onto the surface as well. And this global magnetic field, which is really fascinating. So these green lines are a model of what the magnetic field of Ganymede probably looks like if we were able to see it. So it's a bit like putting a bar magnet under a piece of paper and scattering iron filings on it. The inside of Ganymede has got a magnet as well, and instruments on JUICE will tell us more about the strength and the direction of the magnetic field. So we do have some recent observations of Ganymede, actually. So the Juno mission, which isn't designed to study the moons of Jupiter, actually went past Ganymede 2 years ago. And this is a high resolution view of the surface of Ganymede. You can see many more impact craters on this moon than on Europa. So it's an older surface, but not completely covered in impact craters, which means that it has been resurfaced at some point in the past. So next we get to Callisto. So Callisto, very different to the other three Galilean moons. Arguably, it's boring, but it's also very important for understanding the changes that have happened on the other three moons. So it looks like Callisto hasn't really changed since it was formed. It's just sat there orbiting Jupiter and has been bombarded over time. Maybe there's a subsurface ocean, but it's probably very, very deep. And the JUICE will try to measure or detect the subsurface ocean to see whether it is present or not. But because we have Callisto there as well, which we believe hasn't changed much since it was formed, except for being hit by many other bodies, it's important to have that to be able to compare to the other moons. So here's a global view of Callisto covered in impact craters, large and small. And the closer you look, the more and more craters you see. Although it won't be as fascinating as Europa and Ganymede will be, Callisto is very important in itself. And before I go on to talk about other things, I should mention that JUICE will not be going close to Io. So Io is this volcanic moon. Jupiter is surrounded by radiation belts. So these are regions around Jupiter where there's lots of radiation, so it can actually damage the spacecraft. Many of the instruments wouldn't be able to operate properly. So you can either shield your spacecraft, so basically carry lots of metal up to surround all the instruments so they can operate okay, which is what they did with Juno, or carry more instruments with less shielding, which allows you to do a wider range of scientific observations. But unfortunately, we can't go close to Io because of that. We're too close to Jupiter, and many of the instruments wouldn't be able to work. So it was a balance between fewer instruments, but shielded, or more instruments and less shielded. And it's the latter path that's been chosen for JUICE. So we will be observing Io from afar, but we won't be having any close flybys of that moon. So this is an ESA slide which sort of summarizes what we hope to learn from the Galilean moons. So Europa, Ganymede, and Callisto are being referred to as ocean moons. So under the surfaces, we believe there's a layer of liquid water. So on Europa, we're pretty certain it's fairly close to the surface. And Io and Europa also can be regarded as rocky moons. So the interior of Europa is believed to be a rocky core, and Io we can see rocks at the surface as well. It's too hot to have any water ice on the surface. We know that Io and Europa, well, Io is definitely active with lots of volcanoes, and Europa is probably active as well. So we'll learn about those processes. So from Callisto, we have this body that's just been battered over time and hasn't changed much. So from that, we can learn about the origin and formation of the moons of Jupiter. From Io, we can learn from a safe distance how the volcanoes are driven by these tides, etc. And on Europa and Ganymede, we have this tantalizing possibility that Europa especially may be a place where life has developed. So under the surface, under the crust of Europa, there's a liquid water ocean. We know we have liquid water, we know we have heat, and we know we have lots of chemicals in that water as well, including salts. And maybe life developed under the icy crust of Europa. So JUICE won't be able to detect life if it is there, but it will tell us more about how habitable Europa is. Could it be a place where life could have formed and might be there right now as well? So that's the last question here, the search for life. So JUICE, as well as studying the moons, is going to study Jupiter's magnetosphere as well. So I mentioned before, Jupiter's got a global magnetic field, like a big bar magnet, and it extends really far into space. It's the strongest magnetic field of all the planets. If we could see it from the Earth, it would be bigger than the moon, as shown here on the left. And as Jupiter rotates, it sweeps past the moons and carries lots of ions and electrons, some of them very energetic and dangerous to any astronauts. And from JUICE's observations, we'll learn more about how these moons interact with the magnetic field of Jupiter and the particles that are embedded within it. So on the right here, we can see that Jupiter's magnetosphere is huge, and Pioneer 10 crossed Jupiter's magnetotail, the tail of this magnetic field, and saw that it extended beyond the orbit of Saturn. So related to this, we have aurora. So just like on the Earth, where we have northern and southern lights, including quite recently, coming down to UK latitudes, Jupiter has aurora as well. It has its global magnetic field, and this interacts with this flow of particles from the sun called the solar wind. So many of JUICE's observations will be to learn about Jupiter's atmosphere and its aurora. This is a view of the aurora taken from the Hubble Space Telescope around Earth. So this is an ultraviolet picture. And you can see this sort of oval around Jupiter's north pole. And then on the right, you can see what looks like a little tadpole. And that's where one of the moons of Jupiter is connected along magnetic field lines to the top of Jupiter's atmosphere. So there are 3 instruments on JUICE that will be able to observe the aurora in ultraviolet light, in infrared light, and in visible light as well. And we know from observations with observatories around the Earth that the aurora is also a strong source of X-rays as well. So we'll learn more about what drives these aurorae and why they give off light at these different colors and wavelengths. So this is a very busy slide, but we're going to use different instruments on JUICE as well to study Jupiter's atmosphere. So already mentioned, we'll be able to look in the ultraviolet, the infrared, and at longer wavelengths, so microwave wavelengths as well. We also have a visible camera, of course, taking pictures of the clouds, etc. And with this range of instruments, we can deduce, we can basically see what gases are there in the atmosphere, how they interact with each other. We can also measure the heat coming off the cloud tops of Jupiter and at different depths. And so we'll learn about how the complex atmosphere of Jupiter interacts. You see it's formed into these bands because Jupiter rotates so quickly, and these bands are alternating rising and falling air in Jupiter's atmosphere. So I won't go through this in detail, but JUICE is basically carrying instruments that are going to tell us a lot about the planet Jupiter itself and the moons as well. So it's got some instruments that taste the environment around the spacecraft itself and measure the magnetic field, etc. And it has remote sensing instruments, so cameras working at different wavelengths that can see these moons and the planet from a great distance as well. So observing things from fairly close range with these cameras and other remote sensing instruments, and also sensing the particles traveling past the spacecraft as well. So I'll show a movie from ESA now. So I just have to move a window so I can see what I'm doing. So I'm going to play a movie now from Jupiter, from ESA, showing the JUICE mission. So I may skip forward a few bits as well. So if all goes well, on April the 13th, JUICE will be launched, and you can see it leaving the Earth. So you can follow it now just close to the Earth there. So it's going to travel around the Earth, and it'll actually come back to Earth in 2024. We'll whiz past the Earth, and the Ariane 5 rocket that will launch JUICE doesn't have enough power to send it all the way to Jupiter in one go. So JUICE is to take this long trip, traveling past other planets, and each time it passes the Earth and Venus, it's robbing a little bit of momentum from these planets. So JUICE will speed up a little, and the planets will slow down by a tiny amount, an amount too small to measure. So it's going to basically rob Earth and Venus of a bit of extra energy to eventually allow it to get out to the distance of Jupiter. So it's going to have these orbits past past Venus and Earth, and the one in January 2029 is, as you can see, we're seeing a better view here of what it's going to look like flying past the Earth. I'm sure many amateur astronomers will get to see JUICE before it takes that last part of its trip out to meet Jupiter. And then in July 2031, it'll reach Jupiter itself, and then we'll fire its engines to go into orbit. So it'll carry out several flybys of Ganymede, as you can see here. The first of 12 flybys, and then this is sped up now, and then it'll go into orbit and will travel around Jupiter for several years. So I'm going to step forward a little in the interests of time. Oops, too far. Okay. Yeah, so one part of the orbit will take it out of the plane of the moon's orbit, so it'll be able to look down at the poles of Jupiter. And then the exciting part of the mission for many scientists is JUICE going into orbit around Ganymede. So at the end of the mission, it's not just going to be orbiting Jupiter, it's actually going to go into orbit around Ganymede, the largest moon, the one with the global magnetic field. And it will spend quite some time orbiting Ganymede, so we'll have fantastic high-resolution maps of this moon, also measure the magnetic field and what the particles are doing around this moon. And by observing it over time, we'll be able to see changes in how the magnetic field of Jupiter interacts with Ganymede. So I'll quickly whiz through the instruments. So JUICE is a really big big spacecraft carrying lots of different instruments. As I mentioned, some are remote sensing, looking at things from afar, others are in situ. So the remote sensing ones include the main camera. So I put as the audience is primarily in the UK for this talk, I'll just highlight where there's a UK contribution to instruments. So the Open University provided the detectors, which were built by Teledyne E2V in Chelmsford for the Janus camera. Also have infrared instrument and ultraviolet spectrometer that the University of Leicester is involved in on the science side. And then if we move on to geophysics instruments, we have a laser altimeter that can measure precisely how far JUICE is above the surface of the moon. It's got a radar that will be able to penetrate the ice and see under the surface. And then radio science instrument, which will use radio signals to the Earth to measure how fast it's going. And then we have in situ instruments. So the JMAG instrument is a magnetometer. So that's a very sophisticated compass, and that's led by Imperial College London. So we at MSSL have contributed to PEP, which is a package of sensors that are looking at the particles around Jupiter and its moons. Yeah, these contributions to instruments has been funded by the UK Space Agency. So all these instruments are consortia, so it's groups of many universities and other institutions working together with the UK providing hardware to several of them, and involvement in the science teams of several others as well. So very briefly, because we want to find out whether these oceans on Europa and Ganymede can harbor life, how can we detect these subsurface oceans? Because we're not landing, we're not going under the surface. So there are different techniques. So the magnetometer, JMAG, can measure the magnetic field around these moons. Because the oceans are believed to be salty, as Jupiter's magnetic field is going past these moons, it basically drives currents, electrical currents in these salty oceans, and we can detect those signatures. We can also detect the changing shape of a moon's surface with the laser altimeter, and by learning how that shape changes over time, we can learn more about the interior. And then the changing gravitational field as well can be measured too. And then finally, we can observe aurora on the moons as well. It's not just Jupiter itself that has the aurora. So Ganymede has aurora as well, and we will be able to observe those. And if they move, then that's a sign that under the surface of Ganymede we have a liquid ocean. So it's not just JUICE that's going to the Jupiter mission. There's also a NASA mission called Europa Clipper that's going to launch in October next year. You can see it being built there at the lower right. So they'll be arriving at roughly the same time. So one particularly interesting thing is that we have two spacecraft orbiting Jupiter at the same time. They won't always be close to each other, so the distances between them will vary, but with these two spacecraft, we'll be able to get lots of extra information. You know, if we make one observation with JUICE in one location and Europa Clipper sees something else elsewhere in the magnetosphere, we can put the data together. So the teams of these two missions are already starting to work together and planning these joint observations. Oops. And as an example of this, the JUICE flyby of Europa in 2032, the two spacecraft will be quite close together then. So you can see them coming in on the left. So this busy rotating thing shows the magnetic field lines of Jupiter. So this rotating magnet that's inside the planet Jupiter, and these two spacecraft will be making measurements at the same time, fairly close to each other, while close to the moon Europa as well. So launch is approaching. I won't go through this plot in detail, but basically ESA have chosen 13th of April as the best time. They could launch a little earlier, but then they wouldn't have as much fuel when they get to Europa. So they've gone for a date where they've got the best chance of having extra fuel when we get there. So if they launch before 23rd of April, then there will definitely be enough fuel left to be able to go into a very low orbit around Ganymede as well. So JUICE is already at the launch site, the rocket is almost ready, and the launch is less than 2 weeks away as I speak now. So Thursday, 13th of April at 1:15 British summer time. So this is what JUICE looks like now. It's at the launch sites. There it is on the left. You can see these engineers in their clean room suits to keep the spacecraft clean of dust and other debris, so you can get a sense of scale of the spacecraft. And then on the right, there's the Ariane 5 rocket. So it's almost the last Ariane 5 launch that will carry JUICE into space. So after JUICE gets into space, I'll fast forward here again. It'll unfurl itself, the instruments will open out. So after getting into space, the next few months will be spent on switching on the instruments, testing that they all work, and checking that everything is ready for operating at Jupiter in a few years' time. So to return to the title of the talk, what will we learn from JUICE? A huge amount. So so the main overall questions are going to be like, what are Jupiter's ocean worlds like? So Europa and Ganymede primarily. Why is Ganymede so special? Why has it got a magnetic field? Could there be or ever have been life in the Jupiter system? So Europa is definitely the most promising place. How has Jupiter's complex environment, so its magnetosphere, basically shaped its moons and vice versa? And when we look at Jupiter itself, what is a typical gas giant planet like? How did it form and how does it work? So the data coming from JUICE will help us answer those questions. And as I've added, we'll gather a wealth of information on other topics as well. So because of the time available, I haven't touched on the small moons of Jupiter. There are many dozens of those. We'll get images of those as well, and the rings of Jupiter too. And based on previous missions like Cassini, we'll inevitably find things out we didn't really think of asking. So the long wait for data, we're not getting there till 2031, will certainly be worthwhile. So before going to the final slide, just like to acknowledge the support of the UK Space Agency. So all the contributions from the UK to the mission funded by the UK Space Agency. And I'd also like to thank Olivier Routas, the ESA project scientist, for several of the slides you've seen in the past hour or so. Finally, this is what's going to be on the side of the rockets. There was a competition won by an 80-year-old Yarina a year ago. So that fantastic artist's impression of Jupiter will be on the side of Ariane 5 in 2 weeks' time. And if you want more information, if you search for ESA JUICE mission, that will take you to the right place.